Okay, we're going to have a look now at one of the two permeability tests that we are conducting as part of our soil mechanics labs this semester. This test is the falling head permeability test, and it's conducted on soils that can have very low permeabilities. In fact, you can use it from fine sands, which are reasonably permeable, right down to materials like clay, which let very little water through at all. They're virtually impermeable. So the permeability test, falling head permeability test here, measures how long it takes water to drop down a 5mm diameter tube and flow through a soil sample which is contained in a cell in a reservoir which is filled with water. So the soil is actually in water the whole time, and the water from the tube will drain down through it and into the reservoir. We'll be seeing that in a moment. And we look at permeability and soil permeability because it affects the way soil behaves in construction. It's a cause, for example, of quicksand or quick conditions, which can cause loss of equipment and machinery. In this case, it's an excavator that's been buried on the beach, just because of the balance between the permeability of the soil and the hydraulic uplift due to the water pressure. So let's take a look at the apparatus we're going to use. And here we have the reservoir, which, as you can see, it's a transparent perspex reservoir filled up with water, and inside is our sample. We'll come back to that in a moment. The sample has been prepared inside a 100mm diameter cell. So that's what we have here. This is the same type of cell. This one is a perspex cell, and you can actually use, in this experiment, you can use the sampling tubes that we take from borehole investigations taken as part of a ground investigation. So the sample is contained inside the cylinder. This one is a sandy material, and it's ideally kept in an undisturbed state. In other words, it's taken in the same condition as it was originally retrieved on site. A small filter membrane is put here. That's just to stop any sand escaping. And then the cell is fitted over the top of that. The cell lid is fitted over it like that, and tightened down. And there's 3 screws there to tighten it down. And that's sealed and then immersed and soaked into the reservoir so that all the air bubbles come out. Let's just put that aside and take a closer look at the actual sample. So I've prepared a sample here that's a kind of a silty type material. It's actually a fine ground shale. It's referred to as a clay, but it's not strictly speaking a clay. It's a fine ground shale, and it's inside the cell here in the water, underneath the water level in the reservoir, and the water that's going to drain into that, and we're going to use the measurement permeability, comes down through this tube here. So let's take a look at the and I'm going to move the camera in a bit closer here because it's quite difficult to see what's happening. We've now added the dye to the water, and you can just see on the 5mm tube here, the water is at this level here. It's a green, a yellowy green dye. So this tube is now filled with water, but the valve into the cell here is closed. The initial height of the water, I just took a note there, is 63 centimetres, and an extra 30 centimetres to add on from the base of the meter stick to the water. That's actually a 93 centimetre starting point. I'm going to do now is open the valve into the cell. This will allow the water to drain down into the soil sample below. And at the same time, I'm going to time that. So I have my timer here, stopwatch, and we'll just set that off to go. And if we take a look back up at the tube, the pitot tube, the water has started to drop. It dropped very slowly, just steadily there. It's in the 50s at the moment because this is a relatively impermeable sample. And we're going to time how long it takes to drop a fixed height. It started at 63 centimetres, and we won't go right to the very bottom down here on the cell. Normally we'd stop it around either 30 or 20 centimetres, but we'll let that run for a few minutes and then we'll come back to it. Now, the water has been falling in the tube now for just over 7 minutes, and we're going to stop the test very soon. The reading on the tube, on the meter stick, is just gone past 31, so I'm going to stop the test when it drops to 30. I think you can see it's dropping very, very slowly, and this is because it's an impermeable soil, not like a sand, for example. So there it is, just reaching 30, and I'll turn off the sample there and stop the stopwatch. And the stopwatch is stopped at 8 minutes and 30 seconds. And accuracy here is not just as critical because it's a long period of time. If it was a fast test, we'd have to be much more careful about measuring the number of seconds. So the key information that we're going to need from the test to do the analysis is that our start first of all, our H0 value was at 63 here, 63 centimeters. Our H1, our final height, was at 30, and the time it took was 8 minutes and 30 seconds. The other information we need is the diameter of the sample here, which is 100 millimeters, and inside in the tube, the height of the sample is 12 centimeters. So with that information, we can then use the logarithmic equation in our notes to calculate the permeability of this sample of more impermeable soil, possibly a kind of a silty type of material. So in the tutorial that's going to follow, we'll do our calculations for a number of runs of the test.